Hey, welcome to the series of presentations on differential equations. So I guess I've got the first burning question up here for you. What is a differential equation anyway? Okay, we're going to do simple ones and look at slope fields. So that's a little bit of a hint at what we're doing here. Here's your first differential equation. It's a derivative of y with respect to x equals 2x. And it's an equation. So down here, can we solve that? What would a solution mean? Well, as with ordinary linear equations, quadratic equations, and so on, a solution is a value which satisfies that. So we want a y which satisfies that equation. Or we might want to draw a picture of it. What's the connection over here with these curves and this differential equation? These look like quadratics. How's that happen? Okay, and can there be more than one solution to a differential equation? Interesting ideas. Come down and let's get started and see what you think. So here you are. Consider this equation here. Okay, dy by dx equals neg x. The solution involves finding the y which satisfies this equation. Okay, what y when differentiated gives neg x? Okay, let's go about investigating it. So here we go. Let's look at two approaches. First of all, let's plot the graph of dy by dx equals neg x. What? What's that mean? We have to go into Hutty's trichotomy here, I think. Let's go back again and say we're looking at the derivative in a couple of different ways. We have our first principles, and then we have the slope of the tangent as an interpretation of what the derivative might mean. And then we also have the instantaneous rate of change. Okay, the instantaneous rate of change. Well, here, if we're plotting the graph, I think we'd be looking at slopes of tangents. So in other words, is it possible to track out with little tangents this function? And if it's equal to neg x, the value of the derivative, the value of the slope of the tangent is neg x. Oh, let's see if we can do that. Come down here and let's have a look. I've got one plotted here for you. Dy by dx equals neg x. What's this mean? Well, let's take it x is 1. Dy by dx would be neg 1. So here's a little bit of a tangent drawn here with a slope of neg 1. So right up here, all the way up in x, for x equals 1, the slope of the tangents will all be like that, neg 1. You saw me do these little tangents when we were trying to find the derivative of sine, drawing little tangents and trying to map out what the shape would be. So I hope you remember that. Come to x is 2, what would be the slope of the tangent? Let's draw some little tangents. Neg 2 is a bit steeper. So these are all neg 2s. And then at 3, the slope of the tangent is neg 3. Can you see it's getting steeper negatively here? And so on. Okay, so come over here. When x is neg 1, neg 1 is plus 1. So we get little tangents here, anywhere there, that have slopes of positive 1 and so on. So this is what's called a slope field. Okay, so we're mapping out the equation dy by dx equals neg x in terms of what it really means. It means slopes because it's dy by dx. Okay, and we can plot out what it must be at various x values. Notice we don't know where the curve is located. So anywhere along x equals 1, it's got to have a neg 1 slope value for the tangent. Let's investigate this a bit further. Come down and let's see what we can do. Trace possible functions which would produce this derivative. So let's say we've got a function going through x equals 0 and that value y equals 1 there. The tangent, it must go there and then here. That's got to be a tangent. See what I'm doing? I'm following the tangents here and I've got to obey the rule. So I'll pick it up there and I can't go across the tangent lines. I've got to follow them there. So See what I'm doing? I'm making sure I don't cross, do not cross the tangent lines, because they've got to be tangents. You can't, tangents touch. Do not cross the slope field lines, okay, because they've got to remain tangential, not cutting. They don't intersect tangents. So over this side, we're coming down, follow, follow, follow the next one, pick up another one, pick up another one. Here we are down here. Pick up another one. I think I'm going a bit off here. It's not too bad, but it should be symmetrical. Okay, so we're going to follow tangent lines, and we're going to keep going. And the idea, of course, is to go as far as, you know, is specified, and you've got to fix it through a particular point. So that would be specified. That's a particular solution. Okay, so get the idea. Are there other possible functions? Yeah, what about one going through 3 here? Come through 3. Okay, come down, come down, come down, come down. We pick up this one. We can find a rough y-intercept. Notice we're not going through any, we're not going across any slope field lines. We've got to obey the tangent property. Okay, see that idea? So you could estimate the intercepts, the x-intercepts of this one. Estimate, of course, very rough. So this is one way of tracing the solution. But the solution is a graph, not a function. It's a graph. We're going to come back and look at that one that was on the first page later on. So we'll look at how to do it algebraically in a minute. So the solutions to differential equations can be a function, or it could be a graph of that function, using the derivatives as tangents at various points. Tricky, isn't it? Interesting though, very interesting. I've got a question for you. How can there be more than one solution? Let's check by doing it algebraically, which is probably what you wanted to do in the first place. The integral of dy by dx with respect to x, you've got to integrate it to get y back again, don't you? Remember, the antiderivative or undifferentiate dy by dx, you'll get y. So y equals this thing, the integral of neg x with respect to x. Increase the power by 1, divide by the new power. So it's neg a half x squared plus, oh, there it is. Is that it? I think so. I think that's the reason. And C gives the answer. Because here you have a whole family of them going through 1 or 2 or 3 or any other point. I might ask you to put it through the point, what? 2 or something up here. Okay, in which case you start drawing there. And we've got to come down, don't cross any tangent lines, link it up here, link it up here, and so on. And I might ask you the turning point of this one. Let's see how good we can do this. Okay, how well we can do it, should be said. Okay, so through here, I reckon we're coming this way, up here somewhere. It's getting hard on the screen now. Okay, so I reckon the turning point is somewhere, let's go here, got to go across. I reckon the turning point is somewhere like that, and the next intersection point is about there. Well, what's that? This is supposed to be through the point 2, 2. Okay, so it's through the point 2, 2. If we put 2 in here, it's neg a half by 2 squared plus c. 2 equals a quarter neg 2 plus c. So it should go through at 4. Oh, I missed out there, didn't I? Should have been up here. Okay, so I've got to be careful with that. I think that's correct. Neg 2 there, add 2, yeah, so it should have been steeper. I've turned it too quickly. See what I should have done? I should have ended up like up there. So there's some inaccuracies here. You've got to be careful there, because I've gone off the line here a little bit. And see here, just there, so I should have done a bit higher and come up like that. and come around and over here like that. So it's not a great way of looking at a solution. Okay, it's not accurate, but it's very full of meaning now. It encompasses the idea that when you integrate, you're going to create a family of functions, all with just differing by the constant. And it's going to give you different positions on the slope field for the derivative. Ah, interesting, isn't it? Okay, come down now and go back to this one, which was on the first page. Screen clippings here from Hayes and Harris Publications, so you should grab their book. So here we are. The derivative is 2 times the x value. So you've got some pretty steep values here for the slope of the tangent. Remember, what we are plotting is the slope of the tangent to the curve in little pieces. So when x is 1 somewhere in here, the slope is 2, fairly steep here, or wherever they are. And whenever here x is 1, all the slopes have to be 2 times 1 is 2, no matter which family member you draw. So they've drawn some here. This would be, well, let's check the solution. Let's integrate. Y would be the integral of 2x with respect to x, which is 4x squared on 2 plus c. So this is 2x squared plus c. So you can see they're pretty steep parabolas here, 2x squared, and the c is the different translations in the y direction. You can see that. There's your original y equals x squared, symmetrical about the y-axis, and you've changed the steepness. It's a stretch or a dilation in the y direction, and then you've translated it up the axis. So the different family members here, using the constant of integration, represent translations in the y direction, up the y-axis. I think I said the x-axis. The translations in the y direction. Okay, do you get the idea? So there's the slope field describing the original differential equation, and here are the solution curves. So a solution may be a graph using this approach, or it may be an algebraic statement of the function. Okay, let's go down and have a go at some. I've got some here for you. Have a go. Right, dy by dx equals x plus 1. What I want you to do is to pause the presentation now and have a go on the slope field, and also have a go doing the algebraic solution. Okay, so pause it and have a go and see what you get, and then I'll do it for you. Okay, here we go. Let's go over here, and dy by dx equals x plus 1. So the integral of dy by dx is x plus 1, integral of x plus 1, which is going to be x squared on 2 plus x plus c. Y is going to be that. So there's our function, half x squared plus x plus c. Now we really need to choose a point through which we're going to make the function go. So I would say I'll go through 0, 1 again here. So we'll start here. We're going to go up and up. We're following the next tangent line. Okay, so it's a bit hard to draw on the screen. It's a bit wobbly there. Okay, so then as we come through here, the slope is there and coming down. The slope is there and coming up. We've got to follow these tangent lines here. Okay, and hang on, I've gone a bit off there, I think. I've got to find the tangent lines. Okay, can't cut across them. So here's a little bit of a wonky bit in here. So we'll come down, I think, more like that. So it's not very accurate. But there's a solution to this differential equation. And it's one of the family x squared on 2 plus x plus c. It goes through here 0, 1. So what would I have there? If 0, 1 is on the curve, 1 equals 0 plus c. So it's a family member y equals x squared on 2 plus x plus 1. We don't ask you to actually do much of that. So at neg 1, what should it be? Y would be a half, take 1 plus 1, which should be a half. Am I any good? Oh, not too bad. There it is there. There's the point. Not too bad this time. We don't ask you to have that accuracy, but it's a little test for yourself. Now you could draw some more like that and test whether the point that you proposed for the vertex actually is close to what the algebraic solution suggests. Okay, come down, you have another one. We'll have a go at another one together here. Okay, dy by dx equals x squared. Let's put it over here. Two ways of finding the solution to this simple differential equation. Integral dy by dx with respect to x is the integral of x squared. So that implies y equals increase the power by 1 divided by new power plus c. So there's our function. I think you can see a cube in here. So let's make it go through 1 again. 0, 1. You have to be told where to start it, obviously. There's a whole family. So hang on, I've got to go this way, I think. I've got to make it smoother. I've just transgressed there a little bit. So here, I would say through there, and pick up this one up here, and on we go. And here, down here, we're going to go there, and pick up something like that to there. Got to go parallel to the tangent lines. You don't actually have to go through every one. You pick one up that is going to line up. Again, not a bad graph of x cubed. Oh well, it's a third x cubed, so it's not as steep as x cubed. Let's test a point. I reckon it goes through about neg 1.5 on the x-axis. So sub in x is 0. Let's have a look here. And x is 0. We've got y equals, oh, not x is 0, sorry, x is, rubbish. X is neg 1.5. Y should be 0. So y is 0. And if we do that, we've got 0 equals, I've chosen a bad one here, neg 3 over 2 cubed on 3 plus c. And so this is what, 27 over, neg 27 over 4 over 8, sorry, so this is 24 plus c. So I reckon if it goes through that point, c is 27 over 4. 27 over 24, sorry, or what's that, 9/8. Okay, so does that check back here? So the c is the translational function, so that should be, oh, it's 1 1/8, I'm a bit out. So I back checked it the other way this time. I subbed in my proposed x-intercept, and that should have been right on it. Well, I'm an 1/8 out there. So you can play around there a little bit. Do you understand what I've done there? I've chosen to substitute in my proposed x-intercept and found my y-intercept where I was supposed to start at 0, 1. It's a little bit out. Have some fun with this. I think it's good puzzle stuff. So you'll have many, how many? Infinite number of solutions. Infinite solutions, aren't there? Because of the plus c. There's an infinite number of family members, all differing by just a constant, which will have the same derivative, have the same slope field, therefore. All right. Let's go down and do a couple more. I hope you're having fun with this. So dy by dx equals e to the x. Let's have a look. dy by dx equals e to the x. That implies the derivative integrated will give us function, which will be that. So y will be integral of e to the x as itself plus c. So the whole family member, whole set of family members here, all differing by a constant. So they will be up the x-axis. This is a x translation, sorry, I did it again, y translation of the graph of e to the x. So let's start it again with 0, 1. Here, if it goes through there, we'll go up here. I'm going a bit off cue there. So I've got to go parallel, parallel. I'll pick up this one, and then this one up here, and another one up there, and then we're going to come down. I reckon it probably comes in there, and you can see parallel, but these are all flat. Oh yeah, that's an asymptote there. Okay, so you can't go across the slope field lines there. So here, that's our graph of e to the x plus 1. Well, no, that's just e to the x, isn't it? Because we're at 0,1, which is the usual. I shouldn't have chosen 0,1 that time. So I should have chosen another one. So it's a bit hard to evaluate, to check a point here. So I won't do that for this one. Too hard to check out e. But let's do e to the x plus 1. If you did e to the x plus 1, it would be in here, wouldn't it? It would be the x-intercept, the y-intercept, sorry, is one more. It's up at 2. So I'm going to go in here. So we come through, and I'll just get rid of this. I think I'm starting to deviate already. So I'm coming through here. Okay, so it's just been translated up by, I'll come in just under, because I'm slipping with the writing on the screen here. Okay, so here, look at what's happening. The new asymptote is up at 1. Oh, where are we? Hang on. It should be up at 1, shouldn't it? So, nope, I've slipped. So I've got to go back. I'm trying to draw y equals e to the x plus 2 on the slope field. So that's up here at 2. Let's just go here. I think that was all right. But down here, let's have a look. We're going to come through here. Oh yeah, I see. Here we go. I've got to get off here at that asymptote. Okay, because it's plus 2, which has gone up to, no, e to the x plus 1 we're drawing, sorry. We're going up to 0, 2, okay, and therefore its asymptote would be at 1. So this is the asymptote here. I nearly missed that. Okay, so you've got to be careful when you start at your point here not to slip off. See, I slipped off and came down too low. Because here's e to the x, which has an asymptote of the x-axis, which is y equals 0. If we go up 1, the intercept will go up there, and this will be the new asymptote. So don't slip off the line. We're fairly lenient in tests and exams on this, because as long as you don't radically go across slope fields like that, it's okay. You've got to try and do it. But there is this check here. Generally, with exams and tests, you don't do this check. If they ask you to draw it on the slope field, you just do the best you can there. Try not to go across slope lines. Okay, let's have a look at another one. And here's one that you can't check. Have a look at this. X e to the x, you can't check that one because you can't integrate it at this stage of your career. So we're going to start, let's start at 0,1 again and try to draw this one now. So 0,1 is basically coming through here, so we've got to go there on that side and follow this on this side. Okay, so we quickly see what's happening. It's asymptotic to there, and it's got to be straight up there. Okay, straight up. Hard to write on the screen actually. So there we have it, and on this side we've got to pick up this direction here. So we're going through, and it looks like an asymptote there now. Okay, so there we have it. Yeah, not too bad. A bit wonky over here, I think, but not too bad. So you can see it's an approximate solution to the equation. It's a graphical solution. The solution is a graph for the solution to a differential equation when plotted on a slope field for that differential equation. Hey, getting the hang of it, it's good fun, isn't it? Rather like a puzzle. Anyway, come down now and let's have a look. at a final one. This is the integral of x cubed, so let's do it here. Integral of x cubed take x dx. So you might pause it and have a go. See what you think. I'll have a go now at doing it. Y equals x to the fourth on 4, take x squared on 2 plus c. So there's our integral. And we won't try to sub in now. I'll just do the same thing again through 1. So 1, it's got to be flat. On either side it's going to go down like that. It's then got to be flat again. And then up here, don't go across there, slipping on the page now, and there's our asymptote, not quite there yet, hang on, coming up here, up, and then it's asymptotic there. Okay, can't go across any. So it should have come up a little bit steeper here. Up here, and like that. Okay, and then down here, we're coming down, pick up the next one, and here we've got to take one up now, going up here, and asymptotic. Okay, it's not too bad, and you could check points. If you put, we will check it then, put in 0, 1, we've got 1 equals c, so y equals x to the fourth on 4, take x squared on 2 plus 1 is a proposed function, and I reckon it goes through at about 1 and half there, so 1 comma half. Does that check out? Let's put 1 in the right hand side. 1 equals a quarter take a half plus 1, which is neg a quarter plus 1, which is 3 quarters. So I'm too low? No, I don't know. Oh no, somewhere in here. That's not bad, I suppose. A half, it should be a little bit higher. So you get the idea. I hope you're getting the idea of this C generating an infinite number of family members. So you can't have a unique solution on a slope field. Got a whole family of them. You have to be told where to start. I've been regularly starting there at 0, 1. Okay, so come down. Let's have a look at what you can do now and have some fun here with some actual problems. Screen clippings from Hayes and Harris this time. So have a go with their book there. So we've got a slope field of 2x. We've seen this before. Draw the solution curve on the slope field starting at the point 0, 1. Okay, and use integration. That's just what we've been doing. So here, dy by dx is 2x, integral, increased power by 1 divided by new power, so it's x squared plus c, simple translation. When x is 0, y is 1, so sub it in, 0 there and 1 there, so c is 1, y equals x squared plus 1 is the solution. But they've only drawn part of the solution there. They should have gone this way as well. Okay, should have done that as well. Okay, so just make sure you do that completely, because I didn't say just draw it for x greater than 0. All right, let's go down and have a look at another one. Here we go. Solve find differential equations here and here. No slope field this time, so this is just solution by straight integration. So there's dy by dx. Y will be the integral of this, so just put y and use a bracket integrating the whole thing. Just remember this is with respect to t now, and so here dy by dt, so here 1 as a derivative as the integral t, and here sine of 2t, integral of sine is going to be minus cos, and so here it's minus, and there it is, minus cos 2t, and divide by a half, and that negative is that negative there. So the integral of sine is neg cos, but cos is a function of function, got to divide by that derivative, plus c. So therefore, negative times negative, you've got this function here. and there's no initial condition. You haven't said it when x is 0, y is something, so you have to have a whole family. So there's a family of them. You cannot evaluate c like we were doing before. What about this creature here? This is different, and you also give an initial condition. So that allows you to specify a unique function, a unique value of c. So here let's rearrange this and get dq by dt by itself. So dividing by t, change it to 1 on t, and root t is t to the half over t, subtraction of powers, neg t to the neg half. So integrating it, you want the integral of this. We've changed the variable to t, that's what that's saying, d with respect to t, and then what can we do? Integral of 1 on t. What function differentiator gives 1 on t? It's ln mod t, and here increase the power by 1 divided by new power. Just noticing neg a half increased by 1 is a half, and then we divide by a half. So dividing by a half becomes 2 out the front there plus c. But when t is 1, q is 4. We're told that, so put 4 for q and 1 over here wherever t is, and we can find that c is 6. Just remember the log of 1 here is 0, and then we've got it. Okay, so our particular solution, it's a unique solution because we've specified this initial condition that when t is 1, q is 4. So you have got a unique solution. All right, are you ready to do some? Come and let's have a look at HC1 from Hayes. So I'd like you to pause the presentation and have a go and see what you think. And I'll show you the solutions in a minute. We'll just go up for the other questions now. 3, 4, 5, 6 and 7. I think it's very, very important to do all of these so you build up your skill level. You must practice. Okay, you might practice in a sport. You'd run around the oval lots of times, kicking the ball, throwing the ball, catching the ball. So you've got to do that with maths if you want to be good. Lots of practice. Okay, here are the answers now. Okay, question 1. Okay, lots of little examples there, check them out. Question 2. The rest of question 2 there, part D, or almost part D. E. Let's go to question 3. We'll go 3 and part of 4. All of 4 there now. And 5. Six. And 7. Well, I hope you have enjoyed your introduction to differential equations. There's a few more parts coming up to this, and it gets very interesting. But for now, it's cheers from me.